So far, you've had a handful of problems, I think, that involve the refrigerant 134A. What's coming is in ME 2134 thermodynamics, there's going to be an entire chapter devoted to refrigeration cycles. And nowadays, a large proportion of refrigeration cycles out here in the world use a refrigerant called 134A. Uh, in the old days, we called that Freon, but the substance is R134A, and that can apply to refrigerators, air conditioners, and heat pumps. And so you might be thinking, in the problems you've had so far, man, the biggest problem is finding the properties like U and H and V, specific volume, at various temperatures and pressures. So what I want to do, I have created a MATLAB file uh, that enables the user, and that would be yourself and myself for my own problem solving applications, to access and determine thermodynamic properties of refrigerant R134A using MATLAB. So let's go ahead and get started, and I'll show you how to use this file and how to access this file. So here we go. Here's a little screenshot of a recharging tank for service providers who might come into your home. And when there's slight leaks of refrigerant, let's say in your air conditioning system, that service provider might come in and give you a little charge up to boost up the system pressure with refrigerant. Now, what I'm going to offer you is two files. One file will be in SI units, the properties of saturated R134A and superheated. And so it's a matter of knowing what the phase of your substance, refrigerant, is, and then using the function calls to get your properties. And you think, wow, what a lot of work. So I will disclose to you that once I completed my steam tables tool, and I hope you go back and look at that video for steam tables, because I'm going to blaze through this particular set of properties. And the reason is I used my steam tables MATLAB file, and I used save as, and I called it a different file name. And so that was my starting point. And so the function definitions, the only thing that is different between that source file, steam tables, and my new refrigerant file is that I had to go in and very carefully replace the value vectors, temperature, pressure, internal energy, enthalpy, entropy, and specific volume. I had to replace all those values with the refrigerant property values. But the interesting thing, the neat thing about phase change substances is the fundamental behavior is the same. It's just a matter of the property values are different. And so in the whole scheme of things, although it was work to create this working tool, property lookups for R134A, it wasn't nearly as daunting a task as starting from scratch. But look, I hope that your skill in MATLAB is good and that you might feel like you'd like to start from scratch on some of your own independent ideas. So let's look at what I'm offering for you on these R134A phase change properties. Okay, and so let's see, welcome to the refrigerant tables. I'm trying to move my Zoom business around here a little bit so I can see my own screen. Okay. Here's the start of this file. So you can see it's the title of the file is R134A prop functions dot underscore SI dot M. So you can see that it's all the units will be in SI. Okay. I start my files with lots of comments. So I talk about Well, what's my source data? Where did I get my data from? Okay. And then some instructions to the user, both to you and to me, on how to use this file that demonstrates the use of the functions. Now, this should look very, very familiar to you if you've been through the Steam tables video. In fact, it's basically a repeat of the functions that are available. And remember, I've designed them to kind of make sense. So let's drop down to one I haven't talked about. Let's say HGT in kilojoules per kilogram degree K. The function name is HGT. So what that is H enthalpy, G, of saturated vapor at temperature T, HGT, H sub G at temperature T. So you can see over here, the input is T in degrees C, and the output is H sub G in kilojoules per kilogram. So I think you see the idea here. On superheated properties, remember that you've got to put in two independent properties, and in this case, either pressure and temperature, or pressure and entropy, or pressure and enthalpy, and then you can see the function name. So the easiest one to understand is HPT, kilojoules per kilogram degree K, where the output is H, enthalpy, and the two inputs are pressure and temperature, HPT. So down here, for example, the last function, TPH. Well, what I'm doing here is we're solving for the temperature given a certain pressure and enthalpy. And it turns out for those people that work in the power industry, well, and also in refrigeration, there are many cases where you're given both pressure and enthalpy, and you've got to figure out the temperature. And that can be a daunting task when you're doing it manually in the superheated tables. This function makes it child's play. Okay, so here's the basic layout again of my R134A table. The beginning part is user instructions and the function list. There's the top part. Okay. The next part is the demo function calls for properties under the dome, saturated vapor, saturated liquid. So saturated liquid and vapor demo function calls come next. The next block would be the demo of superheated vapor function calls, a little more complex. And then finally, the preponderance, most of the file is taken up with the thermodynamic property functions. And so here's the tail end of the file. So you can see that this file, very similar to the Steam tables, ends at around 1,200 lines. So it's a lot of lines in this standalone file. And of course, just the reminder is, I strongly recommend that you don't mess with the property functions that I've created for you and for myself. If you do, you're on your own. Okay, and so here's the screenshot before I try to give you a live demo. The function calls for saturation properties, and here I've cycled one, demonstrate temperature saturation given T. So for example, I know the pressure. I know the pressure of my refrigerant. It's some pressure. At what point does that refrigerant boil? At what point does it become a saturated mixture, saturated vapor? What's the boiling point? Well, I enter my pressure in kPa. Shame on me for not putting the units there. Okay, it'd be a lot better if I'd have put the units. Here's my function call, tsat, the boiling point. I'm just calling it variable, MATLAB variable name tsat. Here's my function call, tsat p underscore degree C. That's the name of the function. And my input variable is p. And then I'm simply preparing my command window output here. Okay, changing a number to a string for the temperature and a number to a string for the pressure. And in my output, my command window output, I'm careful to include units on the numbers. Okay. A lot of students don't like to put units along with their numbers, but I've got to strongly encourage you to develop a habit to include units with your numbers. So students will say, oh, well, all these smart professors, they know what units I'm working in. That's not necessarily the case, but I can assure you that when you go out and you practice your engineering skills on a team outside of academics, there's going to be plenty of coworkers that have no idea what units you're working with. So this is a good time to develop a habit of including units with your values. Okay, we're moving on to demo function calls for superheated vapor. You get the idea. Well, for superheated vapor, you've got to input two independent properties. In this case, I've got a pressure of 155 kPa and a temperature of 5 degrees C. Well, thank goodness I've got my units stated over here in a comment. Here's my function call H. That's what I'm calling my MATLAB variable, output variable H. Okay. It doesn't have to match the function output. In this case, I'm just calling it H for a demo. I'm calling the function HPT underscore kilojoules per kilogram with inputs of pressure and temperature. Here's the function call, and then I'm preparing my command window output after that. So you get the idea. And then here's the command window output, where this would be a demonstration of each of the saturated liquid vapor property function calls. It's a bunch of them, isn't it? Okay. And then here's the command window output with the superheated function calls. And so recognize here for the superheated vapor properties, you're always putting in two independent properties. This case down low, pressure and enthalpy, and I'm seeking out the temperature of the superheated vapor of R134a in degrees C. You see, it's cold. Refrigerant what you'll notice here that the saturation pressure at a very common saturation pressure, 155 kPa, the temperature is much, much colder than H2O. And that's why we call it refrigerant. Formulation of the property functions. Now, I probably need to, rather than going in the laborious details of explaining how a function works, I'll suggest you go back to the Steam Tables video for that detailed explanation. But again, for R134a, this comprises the function PG, in other words, the saturation pressure at a known temperature. Look how little this function is. I'm simply defining the X vector right from the book. I'm defining the Y vector, pressure, and with one single MATLAB command, I'm getting the saturation pressure using the built-in function interp1 with my X vector, Y vector, and input T. As a reminder, double interpolation is far more complex in the superheated zone. You'll notice that all of my function calls involve pressure. So I have to, in my function development, I had to figure out a method in MATLAB by which I would find the straddling pressures, find the two pressure tables that straddle my pressure input, and then figure out that would be one interpolation. And then the second interpolation is interpolating on temperature, going down by rows. Think about those tables in the back of your book. And that's the way I do the function calls for the superheated vapor. Very involved, very complex. Happy to talk to you about how to do that offline. But for right now, I can let you know that the demo works and I've checked it out as best I can. Oh, this is my signal to go live, so I can demonstrate to you how do we download those files and a little demo in MATLAB. Okay, so let me show you how can I access this file? Let's go to Jay's Toolbox first. So here we are in my browser. Welcome to Jay's Toolbox website, jaystoolbox.vt.domains. How do we get to the files, the R134a files we're interested in? Scroll down a little bit and go to Toolbox, scroll down to MATLAB and click. There we go. click MATLAB. So there's one page where all of my MATLAB files are stored. Now, as a reminder, the only way I could post these files out to my website, my web host only allows me to, or it did not allow me to save a .m file. Well, I've saved all these files as .doc files. You have to, when you download them, you will open them up, let's say in Notepad on your PC, and then save as to a .m file to make them a MATLAB file. Let's scroll down to find refrigerant R134A. There we go. So what we're going to look at is R134A props, SI. Just click download, save it to your PC, open it up in your MATLAB, and then here's the English units version of the same thing. So either of those files, download, save as .m, save it to your PC to possess. Okay, let's go to MATLAB for a live demo. I believe I loaded in, yes, I've loaded in R134A prop functions SI. And I've got to move my Zoom windows around so I can see what I'm doing. Okay, I've got it. Okay, here's the starting my reference information, my instructions for the user, the functions that are available in this demo file, both saturated, superheated. And now for the demo, I start my tried and true clearing commands in MATLAB, and then I begin my demo. So for example, let's see. Here, let's look at the boiling point temperature of refrigerant at a known pressure. There's the demo right there. Okay. So you can see what we're doing is the user is entering a pressure of 160 kPa. Again, shame on me for not putting units. Okay. I'm doing the function call. I'm calling MATLAB variable tsat equals the function call with the input P. And then I'm preparing my command window output. So you get the idea. Let's keep scrolling down. So I'm demonstrating the use of all of my saturation functions. And I've just been picking strange values so you know that we're going to have to interpolate. The functions have to interpolate for you to get the results. Okay. And then the next block, of course, is the function call, demo function calls for superheated vapor. Oh, I'm doing a little better with my units definitions in MATLAB. That's the preferred way to do it. Okay. Putting in pressure and temperature and getting out enthalpy. So again, I'm just going to scroll down and show you. Here's a demonstration of all my superheated vapor function calls. And now what's below that? Below that, I've got %%. So I've got a new block in my file. It's the function library. So remember, don't modify anything in the function library. If you choose to, you're on your own. Okay. But my function library, I'm pretty sure, I have a pretty good degree of confidence that these functions work, and they are connected up by way of the function calls in the demo. So let me just scroll down so you can see how simple these saturation functions are. See, with the little dash lines, you can really see that these functions are really pretty small, where I'm simply reading in vectors or defining vectors and then doing a single function call that uses interp1, that built-in interpolation command in MATLAB. Keep scrolling down. Okay, here's the end of the saturated liquid vapor property function calls. And next is superheated vapor functions. And these just go on and on and on. So this is one single function. And there's the end of the function, enthalpy as a function of pressure and temperature. So these superheated functions I'm kind of proud of. They're double interpolations that you would do manually in the back of your book. So you get the idea. So let's scroll on back up top and let's do the demo. All I have to do to run the demo is click my Run button. And I get a lot of output, don't I? So I'm going to make this bigger and scroll up to the top. And here's my command window output, saturated liquid vapor function results. So you can see it's a pretty nice tabulation. And notice in my work, not only am I giving a number, I'm not only putting out a number for the user, I'm tying units to it. So these are my output numbers. These are my input numbers, all with units. So that's a good habit to get into. These are the saturated liquid vapor function calls. And then here are the superheated vapor function call demos where I'm putting in two variables, okay, complete with units, and I'm getting out one variable, enthalpy, complete with units, and on and on. Here's entropy. Entropy is a function of pressure and temperature. Think about, yeah, I've had to do some stuff like that. Well, what's coming up is an entire chapter on refrigeration cycles, and it's my hope that you will find these demo functions and demo MATLAB files useful to you as a time saver. So I think you get the idea. All right, I'm going to minimize this and I'll go back to PowerPoint just to finish up. And you'll have to pardon me while I move my Zoom pictures. And so here's the recap and a reminder, and that is I've got two separate files, one file R134aTables for SI and one MATLAB file for English units. You can use those demo files as a standalone thermodynamic property getter. They should work right out of the box. Or if you want to do some thinking on your own, use save as. So you don't destroy your source file, you save as, and then create some of the, instead of the demo block, make some modifications, either delete what you don't need or add to it, add some comments to it, or tailor that to your own needs without changing those function calls or without changing the function definitions to see how you can explore some of your own ideas in MATLAB to support your thermal, fluids, heat transfer classes. Oh, and the reminder, of course, caution, you really need to understand the fundamentals of thermodynamic phase change properties, like needing two independent properties to define the state, before using the MATLAB tools. You really need to have a good grounding in determining the phase. What's the phase of my substance in the first place, rather than just blindly putting in two numbers in the superheated tables. So you realize that if you put in two values where the phase is not superheated, you're going to get an error message. And so that's dangerous. And if you don't know the fundamentals of how to find the phase of a phase change substance first. And of course, the tip there is utilize those saturated liquid vapor function calls to define your phase first. And that's so think about what you did manually. Think about what you did before you're exploring these MATLAB tools, and depend on that fundamental understanding so that you can use these MATLAB tools as a performance enhancer, not a crutch or a shortcut. So anyway, that's my recommendation. I hope you'll try out one or some or all of these MATLAB demo tools and see if you can use them to your advantage, and see if that can improve your effectiveness in solving thermal, fluids, and heat transfer problems.